So in today's lecture, I will be giving you all the theory of resolvent kernel or reciprocal kernel also you all can say, and one problem on resolvent kernel, because I have already uploaded many problems on resolvent kernel already. You can go through those lectures. Okay, now I'll turn the page. Let me do it. Now resolvent kernel or reciprocal kernel, okay. First I have to consider the integral equation y of x is equal to f of x plus lambda integral from a to b k of x comma t y of t dt, and take it as 1. Now which integral equation it is? Both the limits are constant, right? Here upper limit is constant, so it is Fredholm integral equation, right? Now second one is what? Y of x is equal to f of x plus lambda integral from a to x k of x comma t y of t dt, and take it as second. Okay, consider it as second equation. Now this is integral equation, but which one it is? Volterra integral equation, because upper limit is variable, so it is a Volterra integral equation. Okay, now let me turn the page. Solution of equation 1 and 2 gives me what? The solution of this and this will give me what? Respectively given by what? Y of x is equal to f of x plus lambda. Now I will be writing this equation, this integral equation, in terms of this. Y of x is equal to f of x plus lambda integral from a to b. This is what? Gamma of x comma t comma lambda. This is my resolvent kernel. I denote this as a resolvent kernel. Okay, f of t dt. So this is a Fredholm resolvent kernel. Okay, for the first part I have did this. Now second part is what? Volterra. Y of x is equal to f of x plus lambda integral from a to x gamma of x comma t comma lambda f of t dt. Then this gamma of x comma t comma lambda is called resolvent kernel or the reciprocal kernel. Is that clear? Please do this properly, and I will be solving one problem. Let me start with an example. Find resolvent kernel of the Volterra integral equation with kernel k of x comma t is equal to 1. Here we have kernel k of x comma t is equal to 1, right? Now what I am going to do is, what is my k1 of x comma t is equal to? Nothing but it is k of x comma t, which is equal to 1. Next, k2 of x comma t is equal to t of x, t to x, k of x comma u, k1 of u comma t du. Now what is my k of x comma u? Is nothing but 1, right? My kernel is 1, so this is also 1. So what will remain? Du will remain, right? Now I have to integrate this. Now what is the integral of this? U upper limit minus the lower limit. If I do, what I'll get? K2 of x comma t is equal to x minus t. Upper limit minus the lower limit for this. So I will get this. Now I will be doing k3 of x comma t is equal to integral from t to x k of x comma u into k2 of u comma t du, right? For this one it was k of x comma u into k1 of u comma t, but this is what my k3 of x comma t, so k of x comma u into k2 of u comma t du. Now this is equal to integral from t to x. What is this? Is nothing but kernel of this is nothing but 1, right? K of x comma u is 1. And what is my k2 of u comma t is what? K2 of x comma t is equal to x comma t, x minus t. So what is k2 of u comma t? It will be u minus t du, right? Now this is equal to what? What I will get is k3 of x comma t is equal to k minus t the whole square upon 2 factorial. Okay. Similarly for k4 of x comma t is equal to, what I am going to get is k minus t raised to power of 3 upon 3 factorial, and so on. Okay. Next I'll turn the page. So in general, how I am going to write it as kn of x comma t is equal to x minus t raised to power of n minus 1 upon n minus 1 the factorial. Suppose if this is C, here it was what? 4 is there, right? So if I keep my n to be 4, so what I'm going to get is 4 minus 1 is nothing but 3. And here also it will be 3. So I got in this form, right? Now write a resolvent kernel is equal to, now to find the resolvent kernel we use this formula, okay? Summation of m is equal to 1 to infinity lambda raised to power of m minus 1 km of x comma t. Now let us start with this. Now this implies what? Resolvent kernel is equal to what? I will write in these terms, okay? K1 of this series, write it in this form. K1 of x comma t plus lambda K2 of x comma t plus lambda square K3 of x comma t. If you put m to be 1, you will get 0. So what will remain here? Nothing. So if you put 2, it will be 1. Okay? Lambda raised to power of 1. If you put 2, what it is going to give me? If you put 3, it will give me 2, right? So it will be lambda square. So K3 of x comma t plus so on. Now this implies what? Resolvent kernel is equal to gamma of x comma t comma lambda is equal to, now what is my K1 of x comma t is equal to 1, right? K1 of x comma t is equal to 1. And what is my K2 of x comma 2? X minus t, right? So let me put here. So it is 1, okay? And what? And then put lambda as it is plus lambda. And what is my K2 of x comma 2? X comma t. K2 of x comma t is nothing but x minus t plus lambda square. This lambda square I have written as it is. Now what is my K3 of x comma t? X minus t the whole square upon 2 factorial. Now this I will write it here. And plus so on. Okay. Lambda square x minus t the whole square upon 2 factorial plus so on. Now this implies gamma of x comma t comma lambda is equal to e raised to power of lambda into x minus t. Now how I got this? Using this rule, okay? This is rough part, okay? Now e raised to power of x is equal to this 1 plus x upon 1 factorial plus x2 upon 2 factorial up to so on. So it is in this form. Now what I'll do is e raised to power of x, meaning I will be taking this. So where is my x in here? This upon 1 factorial, no, for this one. So I will be writing this. E raised to power of x is what here? Lambda x minus t. So today I am done with today's solving the example of resolvent kernel, and that's starting the theory part. Okay, and I hope you all have understood. If you all have not understood any of the concept of today's, you all can comment below, and thanks for watching.